Testing 1 2 3. Live stream health. So I can hear myself, but we're not streaming just yet. So let's have a look at that. So that's there. No viewers yet. Screens, mic is on. Stream health is bad. Okay, but viewers may be experiencing minor issues. Well, let's close that down, shall we? Exit. Yes. End meeting for all. Exit. Links. Right. So that's that. Is that any better? Or is that still bad? Turn that off. Live stream health still bad. Turn that off. Live stream health. Right. Okay. So live stream health says it's bad. Right, live stream health seems a bit better. You should be able to hear me now. Hello there, Simon Whiteley here. This is me just setting up the live stream, ready to do a proper live stream in a minute. I'm going to be talking about applying causal analysis based on stamp accident analysis, give you a bit of an introduction, talk about a case study, and then I'm available to answer any questions that you've got. Now, it's been a while since I last did a live stream. I've got some new equipment, lights, microphone, and all that kind of business. So I'm just getting to grips with all of this technology, and then we'll jump in and do the live stream and do the presentation. I am going to try and interact with anybody who's watching, so if you do have any questions or comments, please put them in the comments box below and I'll do my best to get to those. And let's see how we get on. Right, so let's try this button then. Let's see what this button does. So there seems to be a little bit of a delay between what I'm sort of doing on the screen and what's coming out of YouTube. So please bear with me a little bit. Right then, so as I said, I'm going to talk about applying causal analysis based on STAMP, which is CAST, accident analysis. The example I'm using is an engine fan cowl door loss that occurred in May 2013, so actually we're coming up quite close to the anniversary of that particular accident. So if you don't know who I am, my name's Simon Whiteley. I'm a systems safety engineering consultant from the UK. I've got 2 degrees. One of those is a Master of Science in Safety Critical Systems Engineering, and I've worked as a system safety engineer across all parts of the engineering, product and project lifecycle across a variety of industries, including civil and defence aerospace, so large multi-engine, fast jet and rotary wing, air traffic control, weapon systems, defence maritime, defence nuclear, armoured automotive, healthcare and government IT, railways and pharmaceuticals, and then more recently developing that into unmanned air systems, autonomous vehicles and cybersecurity. Now, I offer consulting, training, coaching and support regarding system safety engineering and safety critical project management, but more specifically my niche, my passion is helping people use or take advantage of the stamp-based methods across the whole life cycle, but especially accident and incident investigation, and that's what I'll be talking about today. Now, the basic objectives of this live stream, apart from prove the technology and see what it's all about, is to exercise your mind. And that's because minds are like parachutes, as the saying goes. They only work if they're open. And also to do a little bit of practice, not to solve the case study, and also to provide the opportunity for people to ask questions, especially stupid questions. And then obviously make an offer. I'd like to make an offer off the back of this webinar, which I think if this is of interest to you, will be very relevant and you'll be very interested. Now, there is a lot to get through. It is a focus session, but it is ultimately just to give you a taste for what's possible. So let's see how that's going then. So the live stream seems to be working. The stream health seems to be okay. I've got one person watching. Hello there. How are you doing? If you'd like to type in the comments box and chat to me, that would be really, really cool. So a little bit of context then. So you might be familiar with what's called the diffusion of innovation, and essentially what that is, it's the theory of how, why and how fast new ideas and new technologies spread. And essentially with regards to STAMP, its usage is predominantly in private, behind closed doors, and adoption maturity varies across industries and countries. Now if you're familiar with the diffusion of innovation curve, it sort of makes sense, but if you're not, I'll explain it very briefly. So if you imagine that when a new innovation, a new idea, a new technology comes along, at the very early days there'll be some innovators, early adopters, and they will be interested in new opportunities, taking advantage of new technologies, and they'll be interested in taking risks. So they'll try new things, see what it's all about, with the trust and hope that they get an advantage before everybody else. You know, they can take advantage and capitalise upon that. And then over time, as the innovation, the new technology is out in the open for longer, the market share, the number of people that are actually involved in that will increase. So that'll increase from early adopters to the early majority. And then as time continues, you'll have the late majority and the laggards. Now, STAMP itself is essentially in that early phase, so early innovators, early adopters. And what my personal mission is to essentially move STAMP out of academia into the mainstream and help more and more people take advantage of the approaches so that they can reduce costs, save lives, and ultimately make better products, better services, better operations. Now, over the last number of years, I've done various webinars, various training presentations, and what I've found is I've had people from over 22 different countries from across the globe, over 17 different industries, and those industries I've highlighted there in green and bold, generally they're the industries that are trailblazing with these approaches and getting advantages, getting some real good results from it. Now, most of my work is in aerospace and defence, but as I say, this particular live stream is focused on accident and incident investigation. So if you're an accident or incident investigator or interested in accidents and incidents and their investigation, then this live stream is certainly for you. Now, I will be making an investment offer, as I mentioned at the end of this live stream. Ultimately, the aim of it is essentially to help move us up that diffusion of innovation curve. So STAMP, what is STAMP? Well, STAMP ultimately is an acronym, and it stands for Systems, Theoretic, Accident, Model and Processes. And it originates from Professor Nancy Leveson at MIT in the US, the Massachusetts Institute of Technology, and she wrote about it quite extensively in her second book, Engineering a Safer World. Now, you can actually get a free copy of that from the MIT Press website or that Dropbox link below. But also, she kindly did a webinar with me a few years ago where she described an introduction to STAMP, which you can watch by clicking on the link or visiting the various other videos on my webinar. So STAMP itself has two main parts. It's got a foundation or accident causality model, and then some processes, some analysis and design processes built on that foundation. And that foundation is based on systems thinking, systems theory and control theory concepts. Now, just to sort of contrast the traditional view of how accidents occur and the tools and techniques associated with that, and the STAMP view. So in the traditional view, the realm of what you might be aware of or familiar with Swiss cheese, dominoes and bow ties, essentially accidents are chains of directly related events, and they are due to breached barriers. And essentially what that means is that safety is defined as a management of failures problem, and to prevent accidents, essentially you have to prevent failures. Now, in the STAMP view, STAMP builds upon that and goes further than that, develops that. So it's the realm of what are called control loops and structures. And essentially, accidents involve complex dynamic processes, and it redefines safety as a dynamic control problem. And to prevent accidents, you essentially enforce what are called constraints on system behaviour and interactions amongst system components using what's called a control structure. Now you'll notice that I've used square brackets in this, and the reason I've used square brackets is to really emphasise that when I'm using these particular technical terms, I'm being very specific about it, because obviously we're using a lot of general English terms which are not always obvious that I'm being very specific about a specific definition. So wherever you see square brackets in the remainder of this live stream, just be aware that I'm talking about a specific concept. So as I say, in the stamp view, the stamp accident causality model, the foundation of the stamp-based processes, is essentially based upon systems theory and control theory. And that introduces concepts that include systems, components and interactions, structure, hierarchy, control and feedback loops, emergent properties and constraints. And it's the same basis as the systems engineering discipline. And it covers the traditional view inadequacies, especially human behaviour and human factors, software and complex hardware, no failure, system behaved as designed accidents, new technology and designs with no historical pedigree, such as unmanned air systems and autonomous vehicles. It could also be used for artificial intelligence, but I'm not going to talk about that in any detail today. And it also can be used for dealing with so-called systems of systems or services. So as I say, the main high-level concept is you prevent accidents by enforcing constraints on system behaviour and interactions amongst system components using something called a control structure. Now, a control structure is made up of these basic control loops, they're called, and the purpose of that control loop is to enforce what are called safety constraints. Now, ultimately, this is basically the jigsaw piece. This is the thing that you'll look for as part of any stamp-based assessment, and it's the core sort of concept that you'll analyse and think about. In the traditional views, it's all about failures, whereas in the stamp view, it's very much about the controller's control feedback loops. And then the concept of hierarchical control structures. So this is essentially an arrangement of these control loops, these jigsaw pieces in a hierarchy with a structure, and those different structures, they interact with each other through the form of control actions and feedback, and essentially they enforce constraints on the layers below. So what are the stamp-based processes? Well, there are currently 4 model-based processes. The first is STPA, Systems Theoretic Process Analysis, and that is a hazard analysis. Then there is cast accident analysis, which we'll talk about today. And then there is STECA and STPA-SEC. Now, STECA, Systems Theoretic Early Concept Analysis, is a safety-guided design hazard analysis. And STPA-SEC is a cybersecurity-focused hazard analysis based on STPA. So just a quick overview of cast accident analysis then. So as I said, I'll give an introduction to cast, then I'll talk about the case study, I'll talk about the parts of a cast accident analysis, and then at the end, if there are some people watching, I'm quite happy to do the Q&A. So as part of a standard, very high level, very basic accident investigation process, typically you'll observe the accident scene or the information that's available, you'll then document that information, and then you'll make a plan about how you're going to conduct the accident investigation. As part of that investigation, you'll identify and document some facts, you'll do some analysis of those facts, you'll come up with some findings, you'll make some conclusions, and then you'll make some recommendations for preventing future accidents. Now, the cast accident analysis process fits very much in the analysis phase of the accident investigation process, and that's what we're going to focus on today. Now, in terms of investigation and reporting, one of the things a lot of people say to me about the work that I've done is, Simon, I've seen loads of your videos, I really like your videos, but they're nearly always looking at existing reports and basically retrospectively going back and looking at what's in the reports, as opposed to doing a full-blown cast accident analysis. Now, the reason that is because is essentially that to give an example, give a case study associated with accident investigations, I need a good source of information that everyone can use that's not going to be subject to any legal aspects or any other non-disclosure agreements or anything like that. And existing accident reports, once the investigation has been completed and all the legal aspects have been settled, they're generally good sources of information. You don't have to go and do an investigation and collect some information and facts. You can just use the detail and the facts in the report itself. Now, in the civil aviation industry, there is the ICAO, International Civil Aviation Organization, Annex 13, which defines how investigations should be done and how the investigation should be reported. And generally, you can pick up any typical civil air accident investigation report, and it will contain 4 broad sections: facts, analysis, causes, and then recommendations. And essentially, when the investigation is conducted and when they come to document and write the report, there will be information that's unpublished, there will be other questions that were asked, but that were not necessarily included in the final report. And so when doing a report review using the cast accident analysis process, it is likely that we will find questions to ask, or the trail of the investigation might be in such a direction that it's not clear from the actual investigation report whether that was actually considered. And it's not necessarily because it was never considered as part of the original investigation. It's just that it was probably not published in the formal investigation report. Now, as I say, when you do what I'm doing here, where you review an existing report using the cast accident analysis process, you're obviously not collecting extra facts, so you don't change whether the facts, whether there are more facts or not. But essentially you supplement and build on and go over the top of the analysis, the number of causes or the type of causes, and then of course the recommendations. The stamp-based approach allows you to make more specific recommendations than you would otherwise. Now, if you did an actual cast accident analysis as part of a real investigation, then you may well identify more facts, do more analysis, identify more causes, and make more recommendations. So, cast accident analysis on a page, quick and dirty overview. So essentially what we've got on the page here is what the cast accident analysis process is, very high level. So you identify the losses, you identify the associated hazard or hazards, and then you identify the high-level safety constraints associated with those hazards. You do some control structure modelling, you do some control structure analysis, and it's at that point that you really get into the cast accident analysis. So you look at the components of the control structure and then the structure itself and the interactions amongst those components. And you'll notice again the square brackets there. So that's just to make real clear that I'm talking about specific concepts as defined by the stamp-based approach. Now, the ultimate goal of cast accident analysis is to establish what was the control structure that existed to enforce the high-level safety constraints, and how and why each level of the control structure allowed or contributed to inadequate control at that level, and then make recommendations and suggestions as to what changes to the control structure are necessary so that those high-level safety constraints can be enforced so that future accidents don't occur. Now, obviously, that's presuming from the outset that those high-level safety constraints can actually be enforced, because it may be when you do your investigation using this approach, you might find actually the system as it is might not be able to enforce those high-level safety constraints, and so you can make recommendations that that system is not operated until certain changes are made. So this is the engine fan cowl door loss on the aircraft Golf Echo Uniform Oscar Echo, which occurred at London Heathrow Airport in the UK on Friday the 24th of May 2013 at 07:16 UTC. Now, this was a British Airways aircraft. It was an Airbus A319. Unfortunately, there was no fatalities or serious injuries. Now, this is a picture of the starboard engine, but on the inside of the engine, the view of the engine. So this is the left side of the engine. And you can see that the fan cowl doors was basically bent upwards and then ripped off and detached. That caused damage to the outside of the engine and some of the pipe work, so hydraulics, fuel, and also electrical harnesses. And that ultimately led to a significant loss of fuel and then a fire that ignited. Now, both sets of fan cowl doors on the aircraft were both damaged and ripped off but it was just the right hand side that suffered a fire. It could have been very serious. Now, this particular case study came from one UK air accident investigation report, which is 149 pages, and you can access that by going to that address. And what I'm going to do now is just quickly read through the summary to give you a bit of a feel for what actually happened if you're not already aware. So during the takeoff run from runway 27 left at London Heathrow Airport, the fan cowl doors from both engines detached from the aircraft, damaging the airframe and a number of aircraft systems. The flight crew elected to return to Heathrow, and on the approach to land on runway 27 right, leaking fuel from a damaged fuel pipe on the right engine ignited and an external fire developed. The left engine continued to operate satisfactorily throughout the flight. The right engine was shut down promptly, reducing the intensity of the fire, and the aircraft landed safely. It was brought to a stop on the runway, and the emergency services were quickly in attendance. The fire in the right-hand engine was extinguished, and the passengers and crew evacuated via the emergency escape slides on the left-hand side of the aircraft. The investigation determined that a maintenance error had led to the fan cowl doors on both engines being left unlatched, following scheduled overnight maintenance on the aircraft. The unlatched condition of the fan cowl doors was not identified prior to the aircraft's departure the next morning. A number of organisational factors were contributory to the maintenance error. The operator has since taken action to address these issues. This and numerous other similar events shows that the Airbus A320 family aircraft have a history of departing with the fan cowl doors unlatched. It is also evident that in practice the flight crew walk-around inspection is not entirely effective in detecting unlatched fan cowl doors, and therefore a design solution is necessary. Enhanced methods of detection through design solutions are being considered by the aircraft manufacturer. As a result of this investigation, 5 safety recommendations were made concerning fatigue risk management, fan cowl door position warnings, fan cowl door certification requirements, in-flight damage assessments by cabin crew, and aircraft evacuation procedures. So these are just a few photos that I've snapped from the investigation report. So spookily enough, on the day of the accident, there was an operator, member of staff, wandering around the flight line taking photos of the aircraft. And on this particular occasion, they actually took a photo of the aircraft in the condition with the fan cowl doors not locked, as you can see here. So you can see that the fan cowl door protrudes by about an inch or 25 millimeters, and you can't really make it out in this picture. But in this picture, you can see that the latches are actually visible in the unlatched condition, sticking down. And this is literally just as they'd attached the tug to the aircraft, ready to push back. And this is a better picture in the hangar of the same. So this is the port engine. You can see that 25mm gap, and you can see the latches in the unlocked position. You'll notice that they're a bit of an orange colour because they've been painted with high visibility orange. Now this is just to give you an overview of the actual airfield itself. So Heathrow's got two runways, and in terms of the British Airways maintenance facilities, they had 3 different stores spread out across the airfield. And if you've been on an airfield and driven on an airfield, you know these places are huge, and it can actually take a long time to get between these different places when you're driving around in an airport vehicle at 15 to 25 miles an hour. Now, in the maintenance activity that the maintainers were performing, they didn't have the necessary equipment to top up the gearbox oil for the engines. So as part of this maintenance activity on the aircraft, they had to do a weekly check and a daily check. And as part of that weekly check, they have to check the oil. The oil level was found low, so they had to go back to the maintenance stores to pick up the equipment and tools. And when they went to the various stores, they weren't available, so they ended up having to go to a different store which was further away. And that minor disruption, you might say, contributed to them spending more time going around the airfield, and contributed to them not returning to the correct aircraft when they came to do the maintenance. Now this is just to highlight the position of the 6 different aircraft that they were maintained on that day. So there's position aircraft number 1 there, aircraft number 2, this is the accident aircraft, number 3, number 4, number 5 and number 6. So they were moving around all over the airfield, maintaining and working on different aircraft. And this was during a night shift. Now the aircraft registration markings are sort of printed on the aircraft in a couple of different locations. So one location is above the cockpit that you can see there. And obviously this photograph is taken from a typical adult human sort of position looking up at the aircraft. So it's quite difficult to see that registration mark. And then also on the nose landing gear doors, you'll notice there. And then in the background, you've got the engine. I mean, these aircraft are not huge, but they're not that small either. So if you're working on the engines, especially at night, you're not necessarily going to notice those that well. So in terms of the foundation phase of cast accident analysis, so one of the first things that you do is you define the accident. So in the context of Professor Levison's book, Engineering a Safer World, she defines an accident as an undesired or unplanned event that results in a loss, including the loss of human life or human injury, property damage, environmental pollution or mission loss. So essentially an accident can involve types of losses that are unacceptable to the stakeholders, for example brand damage, and that's quite a broad definition. It's not just, I mean you could if you wanted to focus primarily on human health and safety, but it sort of makes sense from a management perspective to look more broadly than that and consider second order effects. So in this particular case we had an aircraft that was damaged, there was fire damage, fuel, hydraulics loss, etc. But there was significant potential for multiple deaths, total loss of aircraft, multiple deaths or injuries on the ground, and damage, loss of assets on the ground. Now, of course, there was also second order effects, which are that the share price was devalued, negative media coverage, brand damage, second victims, so-called second victims, and airport and ATC disruption. So obviously Heathrow is a huge airport which serves a lot of aircraft, and for one of the runways or two of the runways to be blacked is quite a considerable disruption. Now, what other accidents, losses, unwanted outcomes can you think of? So then once we've defined the accidents, we then go on and define the hazard, and you'll notice I've used the square brackets again, and I really need to emphasize this. The English word hazard is used by a lot of people across different types of safety and health and safety, and that English word can be defined very differently. Now there is a general definition of a hazard which is very broad and very loose, and essentially it is something that something that has the potential to cause harm. And that could be, pretty much anything. I mean, that's such a broad, unhelpful definition that you end up trying to manage everything but manage nothing. And so Professor Levison defined the hazard in the context of her book and stamp overall as being a system state or set of conditions that together with a potential set of worst case environmental conditions will lead to an accident. And hazards can be defined in terms of events, time limited, or conditions or states. And it's really important to recognise that this is quite a narrow definition of a hazard compared to the traditional definition of a hazard that most people use. And one of the main reasons for that is to be clear that as a system designer, system operator, you need to control and manage what's within your sphere of control and influence. In the context of air traffic control, if you were to say that a mountain range is a hazard, that from a management and design perspective, that's meaningless because everything is a hazard. What we're concerned with, what our real hazard is, an event or a state, is when an aircraft is in proximity to that unsafe proximity or has an unsafe trajectory in combination with that physical mountain range or whatever it is. And obviously we have some level of control over the trajectory of the aircraft and the proximity of it to that ground terrain. So we define the hazard. In this case I've defined two. Number one is aircraft released for service in an unsafe condition, and the second is that the fan cowl doors were not closed and secured for or during flight. Now the high-level safety constraints associated with those hazards are essentially transposed constraints or requirements in the context of the control structure, those control loops you saw earlier on. So high-level safety constraint number 1 is that the control structure shall prevent the release of an aircraft for service in an unsafe condition. And then the second 2 are that the control structure shall ensure that the fan cowl doors are closed and secured before flight, and that the fan cowl doors remain closed and secured during flight. Now you'll notice for those second 2 high-level safety constraints that I've defined them around the context of closing and securing before flight, but then also that they remain closed and secured during flight. And when you think about what the control structure might look like for those 2 constraints, clearly when the aircraft is on the ground, you've got people involved that are doing maintenance activities, you've got pilots and ground crew doing walkarounds, so they should be looking at that and making sure that they're closed and secure before flight. But when the aircraft is in flight, it's more about the design of the aircraft, the airworthiness and certification of the aircraft to keep those doors closed and secured during flight. So you can imagine that those control structures will look very slightly differently. And as I mentioned, CAST's ultimate goal is to establish what was the control structure that existed to enforce the high-level safety constraints, and then how and why each level of the control structure allowed or contributed to inadequate control at that level. So let's jump into the timeline. So the timeline is something that investigators will typically create as part of their normal investigations. It's not peculiar to CAST accident analysis. It's generally good practice as part of any investigation to create a timeline. And in the context of CAST, when you're building your control structure models or trying to do the analysis, by creating a timeline, that can actually help provide some of the information that you need when you develop the control structure model and then start doing the analysis. Now in this case, I've sort of broken it into 2 parts, the 23rd of May and the 24th of May. So the evening and night time of 23rd of May was when the technicians reported for their shift and then started doing the maintenance activity on the various aircraft. The morning of the 24th of the 5th is when that maintenance was disturbed and the extra work was done, and then when the flight crew arrived to take the aircraft for the day's operations. Now let's talk about hierarchical control structure modelling, or HCS modelling. Now I tend to, like I mentioned earlier on, I tend to talk about this in the context of being, playing with a jigsaw, making a jigsaw puzzle. So you're looking for the control loops, which are the jigsaw pieces, and then you're trying to arrange those in a meaningful control structure model. And whilst you're doing that activity, especially part of an investigation, you can actually see where gaps are and where you might elect to go and look for extra information or evidence as part of your investigation. And that essentially highlights that that CAST can actually be used to help not only analyse facts that you collect as part of your investigation, but also show you what type of information you should go and collect, what sort of evidence to look for. As I mentioned earlier on, you've got the basic control loop. They're arranged in a hierarchy, and when you're doing that modelling, when you're using control structures, thinking in terms of control structures, it really helps to organise your thinking and your understanding. And it also provides a natural path to follow, a structure to work to. And for me personally, that's really what the key part to why STAMP is a very powerful approach. And also, if you're working as part of a multidisciplinary team of investigators, instead of all of you basically talking about your own mental model, your own perception of the accident and the facts that are available, when you create a control structure model, you're essentially making that internal mental model explicit on a piece of paper or a computer screen, so that all the investigators, all the analysts can form a common mental model. And not only does that mean that you all understand, you're focusing on the same thing and working together, it means that you're then not missing things and suffering from cognitive biases and things like that. So when you build your control structure models, typically it's good practice to start with the physical process, the physical world, where harm has occurred, energy has been transferred, and then think holistically, big picture. So we start with the physical world, and what are the entities, what are the controllers, what is the structure that is related to that. Now obviously when we do an accident investigation or incident investigation, we're looking at the operational phase, We might also be looking at maintenance, we might also be looking at modifications or changes, and also near misses or other events, perhaps precursors to this particular accident. Now, when you start from that point and then start to move outwards, you might also start to need to think about contributions from the installation, uninstallation, the creation phase, or very specifically the design phase, and perhaps even the overall design concept that is related to the system that you're looking at, that you're analysing, that you're investigating. So this is a very, very high level control structure model that I've created for the operations phase. So you'll notice at the bottom here I've started with the trajectory, the path, which is the physical process that is under the control of the aircraft itself. The aircraft is under the control of the commander, the pilot monitoring in this case, and the co-pilot, the pilot flying. You've got the commander interacting with the cabin crew, and the cabin crew are interacting with the passengers in the cabin area. Now, in this particular accident, as the aircraft took off and the fan cowl doors started to peel back and then break off and detach, there were other aircrew lining up on the runway behind this aircraft as it was taking off, and they saw what went on and they reported it to air traffic control via the radio system. The passengers on the aircraft also looking out the windows, they could hear and see stuff going on, they could see fuel escaping, and they provided that information to the cabin crew. Now the cabin crew weren't able or did not communicate those issues with the flight deck crew straight away, because obviously during a critical phase of flight you've got what's called sterile cockpit behaviours, conditions going on at the time, and you don't really want the cabin crew interfering with the crew taking off at such a critical phase of flight. Now obviously on this particular occasion you might argue that there was a serious situation that would mean that the cabin crew should communicate with the flight deck crew, but they were not able to diagnose how serious the situation was, such that they could then enforce or go and talk to the flight deck crew with urgency. When the aircraft returned to the airfield and landed, the aircraft was turned into wind to avoid the potential for a fire to be blown across the airframe and the escape slides. And the airport fire and rescue service, the fire the fire chief coordinated with air traffic control and the commander via the radio system, and when the aircraft had come to a stop, the commander was getting ready to evacuate, but the fire chief essentially said, hey, you've not shut down the left-hand engine yet, please don't start to investigate until that's shut down. So the commander shut down the left-hand engine, and what that actually did is it actually cut off some of the radios so that they couldn't actually communicate off the aircraft, and so that further delayed the evacuation order from the aircraft. Now you'll notice that in the bottom right hand corner here I've included the maintenance organisation, and ultimately it's the maintenance organisation that interacted with the aircraft overnight, performing the maintenance activity and leaving the aircraft in an unsafe state. Then you've got the British Airways as the operator, and they have an overall charge over the maintenance and operations organisation. Then we jump into the analysis phase. So when we do any kind of cast accident analysis, we always build the control structure model first, because it is a model-based analysis, and then we do the causal analysis in two parts. Now these are not sort of sequential parts. You can do them, depending on the type and the nature of the investigation you're doing, you will do it whichever way you want to do it. But these are the broad parts to it. So you do some component analysis, and then you do some structure analysis. Now, as part of the component analysis, you'll identify some requirements and control actions. You'll talk about, you'll look at explaining actions and behaviours, and then also identify what other questions should be asked as part of the investigation. Now, one of the things that you'll identify as you go through this process of investigation and building the model and starting the analysis is that you will identify the difference between work as imagined, so how the work is supposed to be done, and then how work is actually done, work as done. Now that's sort of really becomes really apparent also when you start looking at structure analysis, So you'll look at the interactions between components, you'll look at the structure, the architecture, the interactions, you'll look at communications and coordination, and you'll look at dynamics and changes evolution. So you'll notice, you'll recall that when we were talking about this, I said that the radio was essentially cut off when the pilot shut the left-hand engine down, and that could be classified as a dynamics and changes in the control structure and an issue with the communication and coordination, which contributed to explains why the action to evacuate was delayed. Okay, so let's have a look. So looking back at the operations hierarchical control structure, so we can, once we've built the control structure model, we can essentially look at each of these components in the structure and start working through this component analysis. So identifying requirements and control actions, safety related roles and responsibilities and safety requirements, constraints, control and feedback ability, actuators and sensors, failures with those items, and then contributory control actions. Then we look at explaining those actions, those behaviours, and that might be explained because of mental model or process model flaws. So in the case of the pilot getting ready to issue the evacuation order, their mental model was inadequate because they didn't appreciate that the left-hand engine was still operating. And then also contextual factors, context within which decisions were made, and then what other questions should be asked. And this is an iterative process, so you'll work from the physical process upwards to the extremities of your control structure model, examining each of these and identifying the various aspects involved in this. Now obviously as part of an investigation you will need a multidisciplinary team to address each of these parts. Now obviously this is a very high level control structure, and this particular accident wasn't particularly complicated or technical, with technical issues, technical causes. But if you did have some issues with the aircraft itself, then obviously your multidisciplinary team would have to look at those aspects. And as I mentioned, then we do the structural analysis, so looking at the structure, architecture and interactions, communication and coordinations, dynamics and changes, evolution, and then the safety management system, safety information system, and safety culture, and then what other questions should be asked. Now essentially that's pretty much a cast accident analysis in a nutshell, very, very briefly. So in this particular accident then, there was an immediate cause, was that the fan cowl doors were not closed and secured following maintenance activity. The aircraft was in an unsafe condition for flight. Causal factors were that the technicians did not comply with the aircraft maintenance manual procedures, fan cowl doors were left in an unsafe condition following overnight maintenance, and the aircraft was signed off as serviceable. Pre-departure walk-around inspections did not identify fan cowl doors on both engines were unlatched. And there were 3 contributory factors. So the fan cowl door latching system design, the latch positioning, reduced conspicuity of the unfastened latches, high visibility paint finish, the technician's decision that further reduced conspicuity of the unfastened latches, so they engaged the latch handle hooks which prevented the latch handles from hanging down beneath the fan cowl doors, so it made them more difficult to see. And there were 5 recommendations, and these recommendations were aimed at the European Aviation Safety Agency, Airbus, British Airways PLC, in the context of the fatigue risk management system, as I mentioned earlier, a modification to the A320 family door unlatch warning system, the changes to the certification specifications. So these are the requirements for the design of the aircraft to include the fan cowl doors in the system safety assessment, and for British Airways to amend as appropriate pilot and cabin crew training with regards to in-flight damage assessment and reporting, so that the cabin crew are equipped to be able to do some in-flight damage assessment and then provide that information to the pilots. And then for British Airways to review evacuation procedures and training to account for leaving the engines running. So you don't want to leave the engine running in future evacuations. So in terms of recommendations, I mean, obviously we've just gone through this really, really quickly, but what other recommendations can you think of that would become apparent by doing this process, by following cast accident analysis? Well, there may be consideration of pre-flight walk-around inspection effectiveness, post-maintenance inspection effectiveness, specific maintainer training, tasks, fatigue, etc. Stop removing the technical logs from the aircraft, change maintenance, shift, tasking and organisation to ensure adequate coordination amongst maintainers, and then perhaps even add in lockout, tagout lanyards to flight decks, implement maintenance shift changes to manage fatigue risk, and then also with regards to passenger evacuation with luggage and personal belongings. Now, there were a number of unanswered questions that came out of the assessment of this particular case study, and that was when the technicians when they returned to what they thought was the aircraft that they were originally working on, they found that their work had already been done. It had been completed. The doors were locked, all the oil was topped up and everything. Now, that wasn't the actual aircraft that they returned to. They returned to a different aircraft which didn't need that work doing or had already been maintained. So there's questions over the technician behaviour upon finding their work done. What did they do? Why didn't they go and find out why apparently their work had been completed? Why didn't they close that feedback loop? Then there's consideration of the maintenance management in the context of schedule, structure and information, fatigue risk management system, pilots and flight crew interactions, pilot and fire rescue chief interactions, pilot behaviour, the left-hand engine was still running, aircraft manufacturer change management decisions. So as I said, there was quite a history of these fan cowl doors being left unlocked and aircraft taking off, but this was the first aircraft that led to such a severe outcome. So there are questions over how the aircraft manufacturer performed and made decisions about change management. And then of course certification requirements and technical standards. So why were the fan cowl doors not included with specific certification requirements associated with making sure that the aircraft wouldn't take off with unsecured fan cowl doors? So just some final thoughts on near misses. So if you have an accident, a near miss or incident, it reveals that the control structure was inadequate, and that's a fact. And when people talk about root causes and root cause analysis, you know, there's quite a sort of focus on, well, there is no one root cause, there's usually many causes all over the place, and if you focus on trying to find a root cause, you're going to miss things that are really important. So being facetious, the only true root cause in this case is that the control structure was inadequate, and that's the same for any accident. And so near misses and incidents are really massive learning opportunities, and they're cheap learning opportunities, especially because people are more willing to speak and give information freely. So if you do have any near misses or incidents, I highly recommend deploying the cast accident analysis approach. So I'm going to make a brief offer now, an investment offer to work with me personally. So I've spent quite a lot of time putting together a 6-part cast accident analysis online foundation training. And that training consists of 6 parts, as I've said. Each part is over 2.5 hours each, regular group Q&A sessions, an undisclosed bonus training session, which is essentially an extra bonus training session where you, as an enrollee, can vote on a topic that's of interest to you, and we can actually work together to work through that as part of a bonus training session. I'll also provide a closed Facebook group, and essentially all of this together is over 24 hours of training time, working with me, working with other people on the course, and personal support. Now, the value of that is £3,500 plus VAT. And this is a limited time offer. It ends on Saturday the 25th of May, midnight. We actually start the course on the 25th of May. Now it was limited to 10 spaces. I've already had 5 people sign up, so there are five limited spaces remaining. That is the price, but I'm not going to do it for that price. I'm actually going to give you a discount of over 75%, because I recognise that whilst this is a very niche training support that I'm offering, as I said earlier on when I was talking about the diffusion of innovation curve, there are a lot of organisations that are not really willing to invest in this new approach. because from their perspective it's untested, it's high risk, all of those other excuses. And so the people that this particular course will be most appropriate to are those forward-thinking people who really understand that the current approach to accident and incident investigation is not really that good, not really that great, and that they identify that this approach could really help them. So the reason I've reduced the price by over 75% is to reach out to individuals who think that this would really help them and really, provide value in what they do as part of their work. So I've put the offer out there at £750 plus VAT, which is a saving of over 75%. This is a crazy offer. A lot of people have said to me, Simon, you must be crazy. You shouldn't be doing it that cheap. The amount of value that you provide is unreal, especially personal access to you as well. People are able to talk to me. I will give you my contact details so we can talk if you have any issues. So essentially, just to sum up then, the offer is a 6-part online foundation training. It takes you from zero to hero with regards to learning and understanding and practicing with cast accident analysis. Each of those sessions is over 2.5 hours. We'll also get regular group Q&A sessions. You'll get a bonus training session, a closed Facebook group. You would have got a 45-minute private consulting call with me, but that was only for the first 5 people. They've already sold out. You will also get a bonus Microsoft Visio symbols pack. And if you like the control structure models that you've seen in here, I actually use Microsoft Visio to create those models, and I'll actually throw the symbols pack in there so you can make your own really cool looking control structure models. And as I said, that's over 24 hours of training time and personal support, and it is a limited offer at £750 plus VAT, limited offer. So if you want to get involved, learn cast accident analysis, start taking advantage of it, supercharging your investigations, finding more causes of accidents and making better, more effective recommendations, you can't get this offer anywhere else, so please sign up today. What I'll do is I'll stick the link in the chat box as well, so you can click on it directly, so you can have a look at that and enroll today. So as I said about the Visio symbols pack, essentially it allows you to create these control structure models. So you get a Microsoft Visio file with a PowerPoint slide pack presentation that shows you how to use those symbols as part of your control structure modeling activities. Now, we've got a couple of people on watching. Hello there, how are you doing? Thanks very much for watching. It's really awesome to be doing a live stream and have some people on there. And I'd really like to sort of promote some interaction. So if you are watching this, please type in the comments box. Let's have a bit of interaction, a bit of talking, a bit of questions. And I'd really appreciate being able to answer those questions for you. So please ask me 2 questions and then let's see how I can answer those. If you're not really that fussed about talking, that's fine. But I'll be closing the webinar, closing the live stream straight after that. Thanks very much for watching. I hope you enjoyed the live stream. Please ask any questions in the chat box below. Yeah, it's been a while since I did a live stream actually. I think the last one I did was, it was either the beginning of 2018 or the beginning of 2017 when I was talking about the Hawaii ballistic missile launch, false launch alert. That was quite a crazy webinar. Yeah, it's a bit different to doing a webinar, because obviously you have people who are signed up to watch the webinar and get involved and ask questions. Whereas when you're doing a live stream, you're essentially talking, well, broadcasting to the world, and people are watching either live or as a replay. It's quite a strange experience. Okay, well, my viewers are not really interacting, so that's fine. If you do have any questions or comments, please go to the link that I put in the description. So this link here at the bottom, In fact, I'll click on that and show you the website. So just bear with me a second. So that should come up on the screen. So this is my sales page. It provides information about what the offer is. There is also a video there that's video replay sales letter, so you're welcome to watch that. The closing date is in 8 hours, 4 minutes, 4 hours, 4 minutes and 18 seconds. As I mentioned, there are only 5 spaces remaining. The closing date is extended to midnight, the Saturday the 25th. And you get those bonuses. Oh, actually, yes, I didn't mention these bonuses. So you'll get the bonus modeling. Where is it? You'll get the symbols pack. You'll also get a webinar recording. So the basis of this particular live stream was on a full over 2 hours training webinar that I did. You'll get that as part of your enrollment. So if you enroll, you'll get that included as well. You'll also get a copy of the slide pack. So the slide pack you saw today is a cut down version slide pack. So you'll get the full over 100 slides slide pack as part of that. And as I mentioned, there was an exclusive bonus for the first 5 people to have a 45-minute private consulting call with me. Unfortunately, the first 5 have gone, so that's now not available. And it's available to buy today in 2 options, 2 investment options. So there is a one-time payment, £750 plus VAT, and then there is a multi-payment if that suits you, and that's 3 payments, 3 equal payments of £300 plus VAT. And but if you go for the one-time payment, you save over £180. Okay, well, I think that's the end of the live stream. I hope that was useful to you. If you, as I say, if you do have any questions or comments, please go to this website. I've included my email address there, so you can actually send me an email, get in touch, and I'd love to get you enrolled on the course. I'd love to work with you. Thanks very much for watching, and I'll see you on the next video.